So in this lesson, we are going to discuss some elementary properties of the Laplace transform. Now, the first we are going to do is the linearity property of the transform. So let's get into this. Let f1 and f2 be two functions whose Laplace transform exists for s greater than a, and let c1 and c2 be constant. Then for s greater than a, the Laplace transform of c1 f1 plus c2 f2 is equal to, so basically we are going to split this function into two pieces of functions so that we have the Laplace transform of c1 f1 plus the Laplace transform of c2 f2. Now, because c1 and c2 are constants, then basically we can pull them out so that we have c1 the Laplace transform of f1 plus c2 the Laplace transform of f2. So based on this linearity property of the Laplace transform, we are going to solve example 1. So let's try that together. We are going to determine the Laplace transform of 11 plus 5e to the power 4t minus 6 sine 2t. So we have the Laplace transform of 11 plus 5e to the power 4t minus 6 sine 2t. So that is equal to, we are going to split this Laplace transform into three transforms. So we have the Laplace transform of 11 plus the Laplace transform of 5e to the power 4t minus the Laplace transform of 6 sine 2t. So that is equal to, now we are going to treat 11 here. Obviously it's a constant. We know that 11 times 1 is still 11. So we are going to pull 11 out because it is a constant, and then we have the Laplace transform of, now 11 times 1 is still 11, plus here we are going to pull out 5. We have the Laplace transform of e to the power 4t minus, we pull out 6, we have the Laplace transform of sine 2t. Now from the previous lesson, we know that the Laplace transform of 1 is given by 1 over s plus we have 5 times, now the Laplace transform of e to the power at is equal to 1 over s minus a. Now in this case we have a to be 4, so we have the Laplace transform of e to the power 4t to be equal to, that is 1 over s minus 4 minus 6, and then the Laplace transform of sine at, we know is equal to a divided by s squared plus a squared. In this case we have a to be 2, so that is 2 divided by s squared plus 2 squared. Now 2 squared is equal to 4. So finally we are going to multiply the constants across. So we have 11 over s plus 5 times 1, 5 over s minus 4, and then minus 6 times 2, we have 12 over s squared plus 4. So this is the Laplace transform of the function we have here, and notice that this Laplace transform is defined for all values of s greater than 4, okay, because of the s minus 4 we have at the denominator here. The values of s, or the value of s, should be greater than 4. Now let's move on to the second example. So for the second example, we are going to determine the Laplace transform of 5t times e to the power negative 3t minus e to the power 12t cos 8t. So we have the Laplace transform of 5t squared e to the power negative 3t minus e to the power 12t cos 8t. So we are going to break this into two functions, okay, or two Laplace transforms. So we have the Laplace transform of 5t squared e to the power negative 3t minus the Laplace transform of e to the power 12t cos 8t. 5 is a constant, so we pull out 5 so that we have the Laplace transform of t squared e to the power negative 3t, and then minus the Laplace transform of e to the power 12t cos 8t. Now to work out this transform, we know that the Laplace transform of t to the power n times e to the power at is given as n factorial over s minus a all exponents n plus 1. Therefore we have the Laplace transform of t squared e to the power negative 3t to be equal to, here we have n to be 2, so that is 2 factorial divided by s minus, we have a to be negative 3, so negative it becomes positive, so s plus 3 all exponents 2 plus 1, and that is equal to, now 2 factorial is 2 times 1, so that is still 2 divided by, we have s plus 3 all exponents 2 plus 1 is also 3. Now again, for this transform, this is identical to the Laplace transform of e to the power at cos bt, and then this is equal to, now the Laplace transform of such a function is equal to, or is given by s minus a divided by, we have s minus a all square plus b square. So the Laplace transform of e to the power 12t cos 8t is nothing but, we have s minus a on top, so s minus, we have a to be 12 divided by s minus 12 all square plus b square. Now b here is 8, so 8 square is 64. So this is the Laplace transform of e to the power 12t cos 8t. Now we are going to fix these two transforms in here. So that will be equal to, so let's write the Laplace transform of 5t square e to the power negative 3t minus e to the power 12t cos 8t. That will be equal to, we have 5 times 2 over s plus 3 all exponents 3, and then minus s minus 12 all divided by s minus 12 all square plus 64. So let's multiply, the constant across. So we have 5 times 2, that is 10. 10 divided by s plus 3 all cube minus s minus 12 divided by s minus 12 all square plus 64. So this is the Laplace transform of the function we have here. Now this Laplace transform is also defined for all values of s greater than 12. Is defined for all values of s greater than 12. So now let's move on to the next property. So for the second property, we are going to discuss the first shifting property. Now if the Laplace transform of a function f of t is equal to capital F of s and it exists for s greater than k, then the Laplace transform of e to the power at times f of t is equal to capital F of s minus a for s minus a greater than k. Now let's take this example. We are going to determine the Laplace transform of e to the power 4t cos omega t. Now comparing these two Laplace transforms, you realize that e to the power 4t is in the form e to the power at, and then f of t is equal to cos omega t. So we have f of t to be equal to cos omega t. Now whenever you have the Laplace transform of a function where the function contains e to the power at, so e to the power at times f of t, so long as you have f of t being multiplied by e to the power at the first thing we are going to do is to find the Laplace transform of f of t. So for this given function, let's try to find the Laplace transform of f of t. So the Laplace transform of f of t, that is equal to the Laplace transform of the function cos omega t. Now this is equal to, we have s divided by s square plus omega square. So this is the Laplace transform of f of t, which is cos omega t. Now the next thing we are going to do is we are going to replace s by s minus a. So wherever we see s in this transform, we are going to replace that by s minus a. Now we have a here, so comparing these two Laplace transforms, we have a here to be 4. So a is equal to 4. In that case, s minus a becomes s minus 4. So wherever we see s, we are going to replace that and then fix s minus 4. Therefore, we say that the Laplace transform of e to the power 4t cos omega t is nothing but, instead of s, we have s minus 4 divided by s minus 4 all square plus omega square. And this is equal to, we have s minus 4 divided by, now let's try to expand this. So we have s times s, which is s square. We have s times negative 4, which is negative 4s. Negative 4 times s, which is also negative 4s. So that becomes negative 4s minus 4s. So negative 8s. And then negative 4 times negative 4 is plus 16. And then plus omega square. Therefore, we have this to be the Laplace transform of the function given here. So basically, this is how to solve the Laplace transform of a function where the function contains a function f of t which is being multiplied by a function of the form e to the power at. So let's move on to the third property. So for the third property, we are going to learn how to find the Laplace transform of a function f of t which is being multiplied by t to the power n. So if the Laplace transform of f of t is equal to capital F of s, then the Laplace transform of t to the power n times f of t is said to be negative 1 exponent n times the n over the Sn of capital F of s. Now n here specifies the power on t, and it also determines the order of the derivative capital F of s. So we have an example here. We are asked to find the Laplace transform of t to the power sine 2t. So let's try that as we try to explain what this property is all about. So we have the Laplace transform of t sine 2t, and that is given by the property that is given by negative 1 to the power n times d exponent n over the s exponent n of capital F of s. Now comparing these two Laplace transforms, you realize that n here is equal to 1, okay, and then f of t is equal to sine 2t. So since n is equal to 1 here, then we say that this is equal to negative 1 exponent 1 times d ds, okay, d ds of capital F of s. So basically we are going to multiply the first derivative of f of s by negative 1. Now how do we find f of s, or better still capital F of s? Now this f of s is nothing but the Laplace transform of the function f of t. So since this corresponds to t exponent n, and then this corresponds to f of t, let's try to find the Laplace transform of f of t. So for f of t equals sine 2t, then we say that f of s, capital F of s, is equal to the Laplace transform of f of t, and that is equal to the Laplace transform of sine 2t. That is equal to, so if you have the Laplace transform of sine at, we know that is equal to a over s squared plus a squared. So here we have a to be 2, so 2 divided by s squared plus 2 squared, and then 2 squared is equal to 4, so simply s squared plus 4. So that is the Laplace transform of sine 2t. So we are going to fix this Laplace transform in here, and then we try to find the first derivative of it, and then we multiply by -1. So let's find ds of 2 over s squared plus 4. So that is equal to, now we can represent this as ds of 2 times s squared plus 4 exponent -1. Now this is equal to, so using the shortcut form of the chain rule, we are going to hold 2 remains the same, and then we drop down the exponent, so -1, and then we try to differentiate what we have in the brackets. So with respect to s, that becomes 2s, this is a constant, so it goes to 0, and then we are going to repeat what we have in the bracket, s squared plus 4, and then we are going to reduce the exponent by 1, so that becomes -2. So finally we are going to have 2 times 2 is 4 times 1, -4 times s, -4s, divided by, we have s squared plus 4 exponent 2. So that is the derivative, or the first derivative, of 2 over s squared plus 4. 2 over s squared plus 4. Now we are going to fix that here. So this will be equal to, we have -1 times -4s over s squared plus 4 all square, and that will be equal to negative positive, so 4s divided by s squared plus 4 all square. So this is the Laplace transform of the function t sine 2t. Now to the next one, we are going to discuss the time shifting property. So let f be a piecewise continuous function on this interval, that is close bracket 0, infinity open bracket, of exponential order. We define a function g by g of t equals 0, where 0 is less than or equal to t, less than or equal to a, and then f of t minus a, where a is less than t, and then we say that a is a positive number. Then the Laplace transform of g of t is given by e to the power -as times the Laplace transform of f of t. Now what this primarily means is that if a function is delayed in time by a, then the result in the s domain, or better still, the Laplace transform of the function, is given by the Laplace transform of the function without the delay, in this case the Laplace transform of f of t times e to the power -as. So given the function g of t, if that function is delayed in time by a, then we say that the Laplace transform of g of t is equal to the Laplace transform of the function without the delay times e to the power -as. So we have two examples here. Let's try to solve the examples so that we can understand this property. So for example 1, we have g of t equals 0, where 0 is less than or equal to t, less than or equal to a, and then 1 when a is less than t. Now, the first thing we need to do is to locate the function without the delay. Now, the function without the delay here is 1. This is the function without the delay. So we have f of t equals 1. And then the next thing is to find the Laplace transform of that function. And then the Laplace transform of 1 is equal to 1 over s, where s is greater than 0, where s is greater than 0. Now in that case, we know that the Laplace transform of the function given, which is g of t, is equal to, we have e to the power negative as. Now a comes from this value, okay? A represents this value, so e to the power negative a times s times the Laplace transform of the function without the delay, which is going to be 1 over s. So we multiply these two, and then we have e to the power negative as divided by s. Now to the second example, we have the function g of t equals 0, where 0 is less than or equal to t, is less than or equal to pi, and then g of t equals cos t minus pi, where pi is less than 1. Now in this example, you realize that there is a delay. So this function has a delay of pi. Now the function without the delay, is f of t equals cos t. This is the function without the delay. However, this function has been delayed by pi. Now, since we have the function without the delay, then we need to find the Laplace transform of that function. So the Laplace transform of cos t is given by, now we know that the Laplace transform of cos at is equal to s over s square plus a square. In this case, we have a to be 1. Therefore, we have s divided by s square plus 1 square, which is still 1. Now, the next thing is to find the Laplace transform of the function g of t. So the Laplace transform of the function g of t is equal to e to the power negative a. So a comes from this value, or a represents this value. So we have a to be pi here times s times s over s square plus 1. Therefore, we have the Laplace transform of g of t to be e to the power negative pi s times s over s square plus 1. Also, to the next one, we are going to discuss the time integrating property of the Laplace transform. So if the Laplace transform of f of t is equal to capital F of s, and it exists, then the Laplace transform of the integral of f of x dx from 0 to t is equal to 1 over s times capital F of s. Now we have an example here, that is for f of x equals sine 2x, we are going to find the Laplace transform of the integral from 0 to t of sine 2x dx. So we have the function f of x that is equal to sine 2x, and we are asked to find the Laplace transform of the integral from 0 to t of sine 2x dx. Now that is given by the formula, that is given by 1 over s times capital F of s. So what we need to do is basically to find the Laplace transform capital F of s. So given this function f of x, we are going to replace t wherever we see x. So we have f of t equals sine 2t. Now let's try to find the Laplace transform of this function that is going to be represented by capital F of s. So capital F of s, which is equal to the Laplace transform of the function sine 2t, and that is equal to, now even before that, we know that the Laplace transform of sine at is given by a divided by s square minus a square. Now in this case, we have a to be 2, so that is given by 2 divided by s square minus 2 square. Now 2 square is equal to 4, so s square minus 4. So that is the Laplace transform f of s. So you are going to plug this here, in place of f of s, or capital F of s, so that we have that to be equal to 1 over s times 2 over s squared minus 4, and that is equal to 2 over s into bracket s squared minus 4. This is the Laplace transform of the integral from 0 to t of sine 2x dx. Now to the next property, the 6th property, that is the Laplace transform time periodicity. So if f of t is said to be a periodic function with period t, that is f of small t plus capital T is equal to f of small t, then the Laplace transform of f of t is equal to f1 of s divided by 1 minus e to the power negative capital T times s, where f1 of s is said to be the Laplace transform of the first cycle of the periodic function. Now we are going to elaborate more on property 6 and property 7 in the subsequent videos. Now just to explain briefly what a periodic signal or a periodic function is. Now a periodic signal is said to be a signal that repeats its cycle over a regular time interval. So looking at this graph, the graph of f of t against t, now this function or this signal, it starts from 0 and then it goes through and then ends at 2 pi, and then it also starts a new cycle from 2 pi through to 4 pi, and then from 4 pi through to 6 pi. Now from 0 to 2 pi is one complete cycle, so that is the period of the signal. It starts from 0 and ends as 2 pi, that is one complete cycle. It also starts from 2 pi and then ends as 4 pi, and then from 4 pi to 6 pi. So the period of the signal is obtained by subtracting 0 from 2 pi, or better still, subtracting 2 pi from 4 pi or 4 pi from 6 pi. So any of them, is correct. So let's say the period of the signal is given by 2 pi minus 0, and that is equal to 2 pi. This is the period of this signal. Now moving on to property 7, we discuss the frequency integration property. So if the Laplace transform of f of t is equal to capital F of s, and if the limit of f of t divided by t as t approaches 0 and then t is greater than 0 exists, then the Laplace transform of 1 over t times f of t is equal to the integral from s to infinity of the function f of x dx. Now as I said earlier on, we are going to discuss extensively these two properties in the subsequent videos. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.